Hello everyone, this recording is for Physics Module 11, which is on waves. And we are, Module 11 deals with sound waves and light waves. So my plan is to cover sound waves in this video, and then next week we will do light waves. So maybe the first thing to do is to define a wave. And this is the definition that your book gives. A wave is a disturbance that propagates through a medium. So the first thing we see is that it is a disturbance. So you all have probably thrown something into a pond or a lake, and you've seen the waves that are created by that. So you can see that there is a disturbance in the water. But just because there is a disturbance, that doesn't mean that there is a wave, because in order to be a wave, it has to propagate, or in other words, it has to move the medium. Okay, so it has to move the medium in order to be considered a wave. So it's a disturbance, but it is a disturbance that propagates or moves through a medium. And as I said earlier, the mediums that we're going to particularly look at today and next week, we'll be looking primarily at air and how, so our medium will be air, although we'll look at some other things, but air and how sound waves and light waves propagate through that medium. There are two types of waves. The first type of wave is a transverse wave. And an example of a transverse wave that most of you have probably seen is an ocean wave. So in a transverse wave, when a wave is a transverse wave, the propagation is perpendicular to the oscillation. So that's saying a lot, but propagation is perpendicular to the oscillation. Okay, so what does that mean? Well, as you know from watching ocean waves, the waves are up and down like this, right? So the waves, the water is moving in a vertical direction, and yet where is the wave moving? The wave is moving toward the shore. So the wave is moving in a vertical direction, but the propagation is in the horizontal direction. So ocean waves look like this, but they're moving in this direction, and therefore that is an example of a transverse wave. Okay, that is contrasted then with a longitudinal wave. And a longitudinal wave is one in which the propagation is parallel to the oscillation. So propagation and oscillation. Propagation and oscillation are parallel. And one really good example of a longitudinal wave is something that maybe you have played with, and that is a slinky. So I'm going to hopefully show you this video. In which I want you to be able to see that the slinky, we don't need the sound here. The slinky is moving longitudinally, or the slinky is moving. It's not moving up and down; it's moving back and forth, and then it's also propagating in a forward direction. So let's go ahead and watch this video. Okay, so you can see there that the longitudinal waves are moving in the same direction that it is propagating. Okay, so that's a slinky is an example of a propagation of a longitudinal wave. When you look at a slinky, and there's a picture of this in your book, what you see is that there are parts of the slinky that get bunched up, and those are called compressions, and those would be considered the crests of the wave. But then there are parts that are spread out, and those are called the rarefactions. And those would be considered.
The explanation for gravity is that feel that curvature and move.
The rarefactions then would be considered the trough of the wave, and we're going to look at this in more detail later. But we see these compressions and we see these rarefactions in a slinky. But the other thing to realize, and I'll show you this in a little bit, is that a longitudinal wave, an example of a longitudinal wave are sound waves. And an example of a transverse wave is light, a light wave. So keep in mind, we're going to be doing sound today, so keep in mind that sound is an example of a longitudinal wave. Before we get any further, let's go ahead and define some parts of a wave, because we're going to need to use these terms. So I've already used this somewhat, but the upper portions of the wave are called the crests. These downward portions are called the trough. And then the distance from crest to crest or trough to trough is called the wavelength. Okay, so from crest to crest or from trough to trough is the wavelength. And then we also, if we draw a line through the middle of this, then probably not exactly through the middle, but the degree to which the wave is above that center line is called the amplitude. So this would be the amplitude of the wave. Okay, so amplitude, 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 and you could measure it on the other end as well. So we see wavelength, and then another variable to consider then is the frequency. And frequency is how many waves pass a certain point or hit a certain point every second. Okay, so if you think about this, you can probably realize that frequency and wavelength are going to be inversely proportional to each other. Because if you have a long wavelength, then you're going to have a low frequency. A long wavelength means that not as many waves are going to pass a certain point in a second. Whereas if you have a short wavelength, your frequency is going to be higher. With a shorter wavelength, then more of those waves will pass a certain point within a second. So with regard to those variables then, we can say that frequency is equal to velocity divided by, and the symbol for wavelength is lambda. It's the Greek letter lambda, and this is for wavelength. Okay, so this formula shows you what we just said, that frequency and wavelength are inversely proportional, and velocity, V stands for the velocity or the speed of the wave. So if we look at this frequency, if we look at the units, we know that velocity is measured in meters per second, and wavelength is measured in meters. So the meters will cancel, and you'll be left with 1 per second, 1 over second. And we have seen previously that 1 over second is equal to a hertz. So frequency is measured in hertz. And we'll get back to this when we start looking at some problems. Okay, so frequency and wavelength are inversely proportional to each other, and frequency and velocity are directly proportional to each other. The greater the velocity, the greater the frequency with which a wave will occur. Okay, so let's start talking then about sound. And as I said previously, sound waves are longitudinal. And the medium that sound waves typically travel through is air, although we know that sound can also move through other mediums because you know that you can hear somebody on the other side of a wall or on the other side of glass. So sound does move through other mediums, but most commonly sound is moving through air. So when a person is speaking, those sound waves are going to move outward in a wave pattern. So what happens is when a person speaks, the air is pushed outward from the source. And when air is pushed, it clumps together to form a compression. Then when you stop pushing it, then the air pushes back, the air moves backward and you get a rarefaction formed. So you get the air is pushed forward, you get a compression, and then when the air is no longer being pushed, then you get a rarefaction formed. And so then we get that sound wave, like we saw with a slinky, where you get a compression followed by a rarefaction, a compression followed by a rarefaction. So it is a form of it's a longitudinal wave. We're not going to go into all of the anatomy and physiology that is involved, but you probably know that with sound, those sound waves will travel through your external ear, and they will hit the eardrum, which is called the tympanic membrane. And when those sound waves hit the tympanic membrane, the compressions are going to push the tympanic membrane inward. But then when the compressions, the tympanic membrane it's literally just a slim piece of tissue. So when these compressions come along, they're going to push this inward. But then when the sound waves cease and the rarefactions come along, it's going to move back the other direction. So you have essentially set up a vibration of the tympanic membrane. It'll go forward and then it'll go back. But then you probably also know that this tympanic membrane sits next to 3 little bones in your ear. So these vibrations that were set up in the tympanic membrane then get transferred to those bones. And then those bones transmit those vibrations to the cochlea, which is a kind of a spiral-shaped organ that's filled with water. So then you get these vibrations set up in the cochlea. The cochlea has nerve fibers, has little hair fibers and nerve fibers and then those all converge on what is called the auditory nerve. And then from there, that information gets sent to your brain, and based on past experiences of sound that you have had, you interpret that sound. So all of this whole process of hearing in the human ear is set up because of these compressions and rarefactions that cause this tympanic membrane to vibrate. So the basic things I want you to remember is that sound waves they're longitudinal waves. Another thing that you should remember, that you should know about sound waves, is that the frequency of the sound waves determines pitch. So, P-I-T-C-H. So high frequency equals high pitch, and low frequency equals low pitch. So low frequency equals low pitch. So therefore, if you keep all that in mind, then you should also realize that a low wavelength will give you a high pitch, and a long wavelength will give you a low pitch. So wavelength would be the exact opposite of these because they are inversely proportional. Okay, so frequency determines pitch. And then one other thing that we haven't mentioned yet is the amplitude. We defined amplitude. In sound waves, what does the amplitude of the wave determine? Well, that determines the volume. So the greater the amplitude of a sound wave, so the greater the push on that tympanic membrane, then that will determine the volume of the sound. Okay, so let's imagine that we have let's imagine that we have I have these at home, and we'll do this when we get together for a lab. But let's imagine that we have those are they're supposed to be identical. I drew one wider than the other, but they're supposed to be identical. Okay, so here's two pieces of pipe, and if we were to blow into these pipes, so we've probably all blown across a bottle and made a sound. So if we were to blow across these pipes, well, the length of these determines the wavelength, right? So in terms of pitch, both of these would generate the same pitch. But you could change the volume of them by blowing harder on one than the other, but the pitch would not change because the wavelength is set by the length of the pipe. Okay, then what if we were to what if we had this? Okay, now what would we see? Okay, so this has a long wavelength. So long wavelength, and this has a shorter wavelength. And what did we say before? If it has a long wavelength, that means it has a short frequency or low frequency. Let's use the word low frequency. A long wavelength means low frequency, and a short wavelength means that there is a high frequency. So which of these would have the highest pitch? It would be the higher pitch would be the one with the higher frequency, and a lower pitch would be the one with the lower frequency. And you've probably done this where you've blown into different lengths of things and seen what the pitch that they make. So high pitch would happen on a shorter piece of pipe that you're blowing into, and a low frequency or a low pitch would happen with the a low frequency would mean that there is a low frequency, low pitch. Okay, now let's look at one more situation. What if we had those two pipes that are again identical in length, so the wavelength is the same, but let's add heat to one. So let's put one in boiling water, and let's put one in ice water, and then let's have you blow on them. What do you think would happen? Well, what would happen is that the one with the higher temperature would have a greater frequency. So higher temperature equals higher frequency, or another word is saying that is it would have a higher pitch. So here, the wavelength is equal in both cases because they're the same length. But when comparing heat and cold, the higher temperature would lead to a higher frequency. And why is that? Well, remember we went back, we said that frequency is equal to velocity divided by wavelength. Okay, so the wavelength is the same in both cases. So how are you going to get a higher frequency? You're going to get that higher frequency because the velocity is going to be higher. So the higher the temperature, you're going to get an increased velocity of the sound. And you might remember from chemistry that when you heat something up, molecules and atoms are going to move faster. So a sound wave it's molecules, and it's made of air moving around. And so when you heat that up, those molecules and atoms are going to move faster, and that's going to lead to an increased velocity. Okay, so there is a formula that we can use then to determine the velocity of sound based on the temperature. And that formula is 331.5 plus 0.606 times the temperature, and then you just have to remember that the units are in meters per second. Okay, so when you put in temperature, you have to remember that the temperature is in degrees C, but we don't put the units in. Okay, so if we take the temperature times 0.606 and add it to 331.5, that will give us the velocity of the sound at different temperatures. So let's go ahead and start with a problem. We'll go ahead and start with example 11.1 in your book. Okay, and that in this it says that when someone sings a standard A, the frequency of the sound wave produced is 440.0 hertz. Okay, so frequency equals 440.0 hertz. If the temperature of the air is 25 degrees C, what is the wavelength? Okay, so we know that frequency is equal to velocity divided by wavelength. So we are told the frequency. We want to find the wavelength, but to do that we need to first determine what velocity is. So velocity, our formula for velocity is 331.5 plus 0.606 times 25, and this is all going to be in meters per second. Okay, so velocity will equal this plus this, and you should get 347 meters per second. Okay, let's look at the significant figures. So the first thing we have to do is multiply this, and when we multiply that, we have to round it to two significant figures, and that means that, so this gives us 15. Okay, so then when we add this to it, because we're adding now, we can only go out to the ones place because this one only went out to the ones place. So then for our significant figures, we can go out to the one place. So 347 meters per second is the velocity. Okay, so let me erase this. So now we have the frequency. We want to solve for wavelength. So I'm going to multiply both sides times wavelength. That gets rid of that, and divide both sides by frequency. That gets rid of that. So we have that the wavelength is equal to velocity divided by frequency. So the velocity we said was 347 meters per second. And we were given that frequency was 440.0 hertz, which is 1 per second, 1 over a second. Okay, so the seconds are going to cancel and be left with meters. So then wavelength will come out to 0.789 meters. We can have three significant figures, so it comes out to 0.789 meters. Okay, so that's given the frequency and given the temperature, we were able to determine the wavelength. Okay, let's go ahead and do on your own 11.1. What is the frequency of a sound wave whose wavelength is 1 meter? Okay, so wavelength is 1.0 meters. And we are to assume that the temperature is 15 degrees C, 15.0 degrees C. Okay, and we want to know what is the frequency. So find frequency. Okay, so we know that frequency is equal to velocity divided by wavelength. We know the wavelength, and we can determine velocity is 331.5 plus 0.606 times 15.0 degrees. Oh, sorry, we don't put that in there. 15.0. And then we just have to remember that that is meters per second. So velocity, let me find where I did that. If we do this math, you should get that the velocity is 3.4 times 10 squared meters per second. So we can plug that in here for the velocity. And the wavelength is, we were given as 1 meter. So meters are going to cancel. You'll be left with 1 per second, which is a hertz. So the answer then is 3.4 times 10 squared 1 per second, or 3.4 times 10 squared hertz. Okay, let's go ahead and do on your own 11.2 before we move on to our next thing. Okay, so in 11.2, what we are given is if a sound wave has a frequency of 501 hertz, so F equals 501 hertz, and a wavelength is 0.697 meters, we are to find the temperature. Okay, so we know that frequency is equal to velocity divided by wavelength. So in order to get the temperature, we need to get the velocity. So if we multiply both sides times wavelength, that gets rid of that on that side. So the wavelength, 0.697 meters, times the frequency of 501, 1 per second, will give us the velocity, and For that, I got 349 meters per second with three significant figures. 349 meters per second. Okay, so now we can plug that into our formula for temperature or for velocity at different temperatures. So we know that the velocity is equal to 331.5 plus 0.606 times t. So if we can plug in, we calculated our velocity as 349 meters per second. So we subtract 331 from both sides. Let me go ahead and erase all of this over here. So 349 meters per second. Subtract the 331 from both sides. Get rid of it on that side. And then if we divide that by 0.606, that will give us the temperature. So 349 minus 331.5, that's going to leave us with only three significant figures. And then if we divide by 0.606, and this means we can only go out to the ones place. So dividing by 0.606, that will give us 29 degrees C, I think. So this, with two significant figures, this will come out to 3.0 times 10 to the 1 degrees C. So when we take this difference between these two here, that will come out to 17.5, but we can only go out to the ones place, so this has to be rounded up to 18, because we can only go, since we're subtracting, we can only go out to the ones place, and then when we divide that by 0.606, we're left then with just two significant figures. Okay, so that is on your own 11.2. Okay, the next thing we are going to talk about then is the Doppler effect, and in order to do that, I'm hoping to be able to show you a video. So let me see if we can get this going. And I'll play this video, and then we will go from there.
Frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect. the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a
Okay, so we are only going to, for right now, we're only going to think about the Doppler effect with regard to sound. So as that video showed, when an object is moving towards you, the sound waves the sound waves that are produced by that object will bunch up near the front and spread out farther back from you. So you will, because of those sound waves are bunched up, they're occurring at a higher frequency, which means means you will hear it as a higher pitch. And then once the object is by you, then where those sound waves are spread out, the frequency is lower, and therefore you will hear it as a lower pitch. So let's look then. There's a very simple formula that we use to determine the effect of the Doppler effect on sound. So that formula is that the frequency observed is equal to the velocity of the sound plus or minus the velocity of the observer divided by the velocity of the sound plus or minus the velocity of the source. And then multiply that times the true frequency of sound. Okay, so what frequency will be heard? It depends on two things. It depends on the velocity of the observer and the velocity of the source, and then you multiply that times the true frequency to get the observed frequency. So the velocity of the sound is just going to be the speed of the sound that the velocity of the sound that is being emitted. So that's going to be obviously dependent on temperature. So you can calculate that if you are given the temperature. And then we look at the observer and the source. So what do these plus and minuses mean? Well, to determine, so you're either going to add or subtract the velocity of the observer or the velocity of the source. And to determine which of those to do, you just have to reason your way through it. Okay, so let's look first of all at the velocity of the source. Okay, so if we know that if the source of the sound is moving toward the observer, what's going to happen? Those waves are going to bunch up, right? So that means that you are going to hear you're going to hear a higher pitched sound. Well, how do you hear a higher pitched sound? Means a higher frequency. So with regard to our mathematical equation, how would we make this be a larger number? Well, the velocity of the source would need to be lower, and therefore we would subtract it. Okay? And then the opposite would be true if the source is moving away from the sound, then we would add to it, because now in that case the frequency that you hear would be lower. Well, how do you get a lower number in this equation? Well, you would divide by a bigger number, and therefore you would add it. And then the same, we could look at the observer and do the same thing. So if the observer is moving toward the sound, then that's going to result in a higher frequency. Well, how do you get a higher frequency? In this equation, you would get a higher frequency by having a higher numerator. So we would add the velocity of the observer. If the observer were moving away from the sound, then we know that the pitch that you hear would be lower. How do you get a lower, in terms of this equation, how do you get a lower number? Well, you get a lower number by subtracting, by having a smaller number in your numerator, so then you would subtract the velocity of the observer. Okay, so let's, that might be confusing, but let's do a problem to illustrate how that might happen. Okay, so let's look at on your own 11.3. And let's see how we can apply this to this situation. Okay, a man has just said goodbye to his friend who has boarded a train. He stands and watches the train as it travels away from the station at 35.0 meters per second. If the train blows its horn with a frequency of 411 hertz when the train is stationary, what is the frequency that the man will hear? So this is the true frequency, and we want to know what is the observed frequency, and we are told that the temperature is 25.0 degrees C. Okay, so the first thing we need to do is we need to figure out what is the velocity of sound to begin with. So we know that velocity is equal to 331.5 plus 0.606 times 25.0. And that is going to be in meters per second. So velocity for that you should get 347 meters per second if we do that math and with the number of significant figures that we can have. Okay, so we know that the true velocity is 347 meters per second. Okay, so now let's go ahead and look at our equation then. We know that the frequency observed is equal to the velocity plus the velocity observed plus or minus the velocity observed, the velocity of the observer, sorry, velocity of the observer divided by the velocity of the sound plus or minus the velocity of the source. Okay, So, and then we're going to multiply that times the true frequency. Okay, so we know that the true frequency is 411. So let's go ahead and put that in there. And we just figured out that the true velocity of the sound was 347 meters per second. Okay, so in both of these cases, both here and here, we will put 347 meters per second. Okay, so then it just becomes a matter of what do we add and subtract in this equation. Okay, so what is the velocity of the observer? This tells us that the observer is standing still. So the velocity of the observer is 0. And then it just becomes a matter of, okay, what the velocity of the source. We are told that the train is moving at 35 meters per second, and it's moving away. So if the train is moving away from the observer, that tells us that the person, the observer is going to hear a lower pitch, which means it's going to be a lower frequency. So in order to get a lower frequency, we need to divide by a denominator that is bigger. Therefore, that tells us that we need to add to that the velocity. So we're going to add 35 meters per second, and that should be 35.0 meters per second. Okay, so 347 plus 35 meters per second, and we will divide that into 347 plus 0, and then we're going to multiply that times 411 hertz. Okay, so if we take this divided by the sum of this, go ahead and put that up here. What we will end up with then is you will end up with 347 meters per second divided by 382 meters per second. So this down here is going to give us 382, and then we'll multiply that times the true frequency, which was 411. So then doing all of that, what we end up with then is that the frequency observed is equal to 373 hertz. So the frequency is lower, meaning that the pitch will be lower, and that makes sense because the train is moving away from the stationary observer. Okay, I think we're going to try to do one more problem. We'll do the on your own 11.4. Okay, so on your own 11.4 tells us that a woman is driving toward a factory to pick up her husband after work. As she travels toward the factory starts to blow the whistle, indicating the end of the workday. If the whistle has a frequency, so the true frequency is equal to 494 hertz, but the woman hears a frequency of 511 hertz, then how fast is the woman driving? And we are told that temperature is 25.0 degrees C. Okay, so the first thing we need to know is we need to figure out what the speed of sound is. So V is equal to 331.5 plus 0.606 times 25.0. Okay, so if we do that, and with our number of significant figures that we can have, we determine that the speed of sound is 346.7. So 346.7 meters per second. Okay, and we can go out to the tenths place on that in terms of our significant figures. Okay, so the woman is moving toward the factory. So that means that the sound waves are going to be bunched up in front of her. So she's going to hear a higher frequency than the true frequency. So when we look at our equation, so the frequency observed is going to be equal to the velocity of the sound divided by the velocity of the sound plus or minus the velocity of the observer and the velocity plus or minus the velocity of the source. Okay, so that the factory whistle is not moving, right? So this is going to be 0. We already, and both of these numbers will be 346.7 meters per second. So we'll put that in here as well. 346.7 meters per second. So then it just becomes a matter of, are we going to add or subtract the velocity of the observer? Well, if she is moving toward the sound, she's going to hear a higher frequency. So in order for this number to be larger than the true frequency, we need to have a higher number on the numerator, which tells us that we will need to add the velocity of the observer. Okay, and we're trying to solve for that, so we'll add the velocity of the observer. Okay, so let's go ahead and so we were told that what she actually hears is 511 hertz, and we're told that the true frequency was 494 hertz. Okay, so then it's simply a matter of solving for this unknown because we know that the velocity of the source is 0. Okay, so to do that, we will add the we'll divide both sides by this 494. That gets rid of that on that side. So we'll divide this by 494 hertz. Okay, so that gets rid of that on that side. And then what do we need to do? Then we just need to multiply that times the 346.7. and then subtract the 346.7. So if we multiply this, that'll get rid of it on this side. So let's see. We take that and we multiply this times 346.7 meters per second. Do all that, and then if we subtract from that 346.7 meters per second, the answer that we will get for that is that she was traveling at 12 meters per second. Okay, so that was a case where with our equation, we had the frequency observed is equal to the velocity of the sound, the true velocity of the sound, plus or minus the velocity of the observer, plus or minus the velocity of the sound, or let's say the source, and then we multiply that times the true frequency. Okay, frequency true. So we said this was 0, so we can get rid of that. We don't need to worry. It would just be the velocity of the sound. And then it was just a matter of, because we know that the woman is we're going to be adding this because the frequency is higher. So to get a higher number, you need to have a higher numerator in your equation. So then all we did then was solve for, we just solve for the velocity of the observer. So did the math that was necessary to solve for the velocity of the observer. So we added it to both sides, which meant that to solve it, we needed to subtract it from both sides. Okay, so I think we're going to stop there. There are some more of those types of problems in the back of the book, in the back of your chapter. So maybe work some of those before next week, and if you have questions, we can go over those at that time. And then next week we will pick up and we will do light waves.